Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on thermodynamics. Previously, we discussed temperature and the different changes of state possible in a substance. Today, we will be focusing on gases and the concept of ideal gas. Are you ready, students? Let us begin. There are several equations that we use to study the behavior of different gases. In particular, these equations are important when describing macroscopic or microscopic quantities of gas. By quantitatively comparing these two, we can generally discover simple and hypothesis-satisfying data. In order to do this, we need to make several assumptions about a given gas, namely that it is an ideal gas. An ideal gas is a theoretical amount of gas that possesses no impurities or foreign quantities that would otherwise prevent us from getting an accurate result. Generally, most gases exist in a state very close to ideal, and as such, ideal gas calculations may be slightly inaccurate in establishing exact values in a unique quantity of gas. However, it is perfect for discovering the general properties of a specific type of gas. In order for a gas to be considered ideal, it must satisfy several conditions. Most importantly, it must satisfy all the gas laws in order to meet the requirement. Boyle's law states that pressure times velocity is constant if temperature is a constant. Charles's law states that volume over absolute temperature is constant if pressure is a constant. The pressure law states that pressure over absolute temperature is constant if volume is a constant. We can combine these three laws into one comprehensive equation. Pressure times volume over temperature is a constant. You may ask yourself, what does the constant represent? This is a very good question, students. Thankfully, experiments have determined that for a given pressure and temperature, doubling the amount of gas also doubles the volume. Therefore, it is safe to assume that our constant can be written as nRT R. In this case, N represents the number of moles of particles in the gas, while R indicates the molar gas constant. The molar gas constant is a constant value given by the pressure times the volume of a gas divided by its absolute temperature. The value of this constant is approximately 8.3 joules per mole Kelvin. From this, we can further elaborate on the earlier equation. Pressure times volume is equal to the number of moles times the molar constant, multiplied by the absolute temperature. This is called the ideal gas law. Let us use this law to solve a problem. Get ready for an activity, students. A student in Addis Ababa is observing a plane as it flies overhead. The atmospheric pressure is approximately 9.2 times 10 to the power of 4 pascals at the ground level. The temperature is 305 kelvins, and the air density is 1.2 kilograms per cubic meter. The airplane is located 4,500 feet higher, where the atmospheric pressure is 7.8 times 10 to the power of 4 pascals. The temperature is 275 kelvins. What is the density of air around the plane?
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, everyone. To begin, the solution is made easier to find if we are dealing with a fixed mass of gas, so it is easier to isolate the density of 1 kilogram of air instead of 1.2. By quickly dividing 1 kilogram into 1.2 kilograms, we discover that the density of 1 kilogram of air is 0.83 cubic meters. Therefore, the value of the variables in the ground level equation is as you see them here. The values around the airplane equation are already known. As the mass of gas stays fixed, we can write the ideal gas equation as P 1 times V 1 over T 1 is equal to P 2 multiplied by V 2 over T 2. Substituting all the values into the ideal gas formula, we will arrive at the answer. The volume of air around the plane is 4.74 cubic meters. This means that the density of our 1 kilogram mass of air is 1 kilogram per 2.1 cubic meters, which is 0.21 kilograms per cubic meter. Was this your answer? If so, great job. Conducting these kinds of experiments allows us to identify the behaviors of a gas in a given system. As gases change because of external surroundings, they go through processes. These are subdivided into different categories to reflect the types of possible changes. The first is an isobaric process. This is a process in which the pressure of a gas remains constant. Thus, any work done by the system results in an increase in volume. This pressure over volume diagram shows a substance increasing in volume at constant pressure and is the diagram that best describes this process. Processes can also be isochoric. In these, the pressure increases while the volume remains constant. For this to occur, no work can be done by the system because the definition of work also suggests a change in volume. Isothermal processes retain constant temperature. Therefore, there is no change in the internal energy of the system. In this case, pressure will decrease as volume increases. Students, it is time for our final activity. You will be provided with a choice of pressure over volume graphs. Can you label each process correctly? You may begin.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back. Here are the correct labels for each diagram. Did you label each correctly? The first diagram is an isothermal process. The second diagram is an isobaric process. The last diagram is an isochoric process. Well done, students. This concludes our lesson for today. Until next time, thank you, teacher. Thank you, students.